Algorithms. Algorithm basics. A password might not be enough to protect your online accounts. Two-factor authentication adds an extra layer of protection. A common form of two-factor authentication sends a personal identification number, PIN, to your cell phone. To log in, you perform the series of steps shown in Figure 1-1. The procedure for two-factor authentication is an example of an algorithm. In a general sense, an algorithm is a series of steps for solving a problem or carrying out a task. Algorithms exist for everyday tasks and tasks that involve technology. Here are some examples. A recipe for baking brownies. The steps for changing a tire. The instructions for pairing a smartwatch with your phone. The payment process at an online store. The procedure for posting a tweet. Programming algorithms. Algorithms are also an important tool for programmers. A programming algorithm is a set of steps that specifies the underlying logic and structure for the statements in a computer program. You can think of programming algorithms as the blueprints for computer programs. A computer program is a set of instructions, written in a programming language such as Java, C++, or Python, that performs a specific task when executed by a digital device. A computer program is an implementation of an algorithm. There can be more than one programming algorithm for solving a problem or performing a task, but some algorithms are more efficient than others. Good algorithms. Computer scientists are interested in designing what they call good algorithms. A good algorithm tends to produce a computer program that operates efficiently, quickly, and reliably. Good algorithms have these characteristics. Input: the algorithm applies to a set of specified inputs. Output: the algorithm produces one or more outputs. Finite: the algorithm terminates after a finite number of steps. Precise: each step of the algorithm is clear and unambiguous. Effective: the algorithm successfully produces the correct output. When formulating an algorithm, you can easily check to make sure it satisfies all the criteria for a good algorithm. You can see how these criteria apply to an algorithm in Figure 1-2. Selecting and creating algorithms. Before coding, programmers consider various algorithms that might apply to a problem. You can come up with an algorithm in 3 ways. Use a standard algorithm. Programmers have created effective algorithms for many computing tasks, such as sorting, searching, manipulating text, encrypting data, and finding the shortest path. When you are familiar with these standard algorithms, you can easily incorporate them in programs. Perform the task manually. When you can't find a standard algorithm, you can formulate an algorithm by stepping through a process manually, recording those steps, and then analyzing their effectiveness. Apply computational thinking techniques. Computational thinking is a set of techniques designed to formulate problems and their solutions. You can use computational thinking techniques such as decomposition, pattern identification, and abstraction to devise efficient algorithms. Let's take a look at these techniques in more detail. Decomposition. Decomposition basics, parenthesis. A mobile banking app contains many components. It has to provide a secure login procedure, allow users to manage preferences, display account balances, push out alerts, read checks for deposit, and perform other tasks shown in Figure 1-3. The algorithm for such an extensive app would be difficult to formulate without dividing it into smaller parts, a process called decomposition. When devising an algorithm for a complex problem or task, decomposition can help you deal with smaller, more manageable pieces of the puzzle. Structural decomposition, parenthesis in parenthesis. The first step in decomposition is to identify structural units that perform distinct tasks. Figure 1-4 illustrates how you might divide a mobile banking app into structural units, called modules. Structural decomposition is a process that identifies a hierarchy of structural units. At the lowest levels of the hierarchy are modules, indicated in yellow in Figure 1-4, that have a manageable scope for creating algorithms. Here are some tips for creating a structural decomposition diagram. Use a top-down approach. The nodes at the top break down into component parts in the nodes below them. Label nodes with nouns and adjectives, rather than verbs. For example, account management is the correct noun phrase, rather than a verb phrase, such as manage accounts. Don't worry about sequencing. Except for the actual login process, the components in a mobile banking system could be accessed in any order. This is a key difference between an algorithm and decomposition. An algorithm specifies an order of activities, whereas decomposition specifies the parts of a task. Functional decomposition, parenthesis. Functional decomposition breaks down modules into smaller actions, processes, or steps. Figure 1-5 illustrates a functional decomposition of the two-factor authentication module. Notice how the levels of the functional decomposition diagram get more specific until the nodes in the lowest levels begin to reveal instructions that should be incorporated in an algorithm. Here are some tips for constructing functional decomposition diagrams and deriving algorithms from them. Label nodes with verb phrases. In contrast to the nodes of a structural decomposition diagram, the nodes of a functional decomposition are labeled with verb phrases that indicate what is to be done. Sequence from left to right. Reading left to right on the diagram should correspond to the sequence in which steps in the algorithm are performed. Object-oriented decomposition. Another way to apply decomposition to a module is to look for logical and physical objects that a computer program will manipulate. Figure 1-6 illustrates an object-oriented decomposition of the two-factor authentication module. An object-oriented decomposition does not produce a hierarchy. Instead, it produces a collection of objects that can represent people, places, or things. Tips for object-oriented decomposition. Node titles are nouns. Each node in the object-oriented decomposition diagram is labeled with a noun. Attributes are nouns. A node can contain a list of attributes, which relate to the characteristics of an object. Methods are verb phrases. Methods are actions that an object can perform. You may need to devise an algorithm for each method. Sketch in connection arrows. Connection arrows help you visualize how objects share data. Dependencies and cohesion. You might wonder if there is a correct way to decompose a problem or task. In practice, there may be several viable ways to apply decomposition, but an effective breakdown minimizes dependencies and maximizes cohesion among the various parts. The principles of decomposition are: minimize dependencies. Although input and output may flow between nodes, changing the instructions in one module or object should not require changes to others. Maximize cohesion. Each object or module contains attributes, methods, or instructions that perform a single logical task or represent a single entity. Pattern identification. Pattern identification basics. The amaze your friends math trick for quickly adding numbers from 1 to 10 is very simple. Get the last number in the series, parenthesis, 10, in parenthesis. Divide 10 by 2 to get a result. Add 10 plus 1 to get a sum. Multiply the result by the sum. Now, what if the challenge is to add the numbers from 1 to 200? That algorithm looks like this. Get the last number in the series, parenthesis, 200, in parenthesis. Divide 200 by 2 to get a result. Add 200 plus 1 to get a sum. Multiply the result by the sum. Notice a pattern? This fill-in-the-blank algorithm works for any number. Get the last number in the series, parenthesis, in parenthesis. Divide by 2 to get a result. Add plus 1 to get a sum. Multiply the result by the sum. The process of finding similarities in procedures and tasks is called pattern identification. It is a useful computational thinking technique for creating algorithms that can be used and reused on different datasets. By recognizing the pattern in the Amaze Your Friends math trick, you can use the algorithm to find the total of any series of numbers. Repetitive patterns, parents. In addition to fill-in-the-blank patterns, you might also find repetitive patterns as you analyze tasks and problems. Think about this algorithm, which handles logins to a social media site. Get a user ID. Get a password. If the password is correct, allow access. If the password is not correct, get the password again. If the password is correct, allow access. If the password is not correct, get the password again. If the password is correct, allow access. If the password is not correct, get the password again. If the password is correct, allow access. If the password is not correct, lock the account. Recognizing this repetition, you can streamline the algorithm like this. Classification patterns. Everyone who subscribes to a social media site has a set of login credentials. Here are Lee's and Prize. The series of attributes that define each user's login credentials have a pattern of similarities. Each user has 3 attributes: a user ID, a password, and a mobile number. By recognizing this pattern, you can create a template for any user's login credentials like this. User ID, password, mobile number. You can often discover classification patterns in the attributes that describe any person or object. Identifying classification patterns can help you design programs that involve databases because the template identifies fields, such as user ID, that contain data. Classification patterns also come in handy if you want to design programs based on the interactions among a variety of objects, rather than a step-by-step algorithm. In some programming circles, a template is a classes because it specifies the attributes and methods for a classification of objects. For example, people classified as social media subscribers have attributes for login credentials. Vehicles classified as cars have attributes such as color, make, model, and VIN number. Businesses classified as restaurants have a name, hours of operation, and a menu. Abstraction. Abstraction basics, think back to the Amaze Your Friends math trick. By identifying a pattern, you formulated a general algorithm that works for a sequence of any length, whether it is a sequence of 1 to 10 or 1 to 200. Get the last number in the series, in parenthesis. Divide by 2 to get a result. Add +1 to get a sum. Multiply the result by the sum. In this algorithm, the blank line is an abstraction that represents the last number in the sequence. An abstraction hides details, simplifies complexity, substitutes a generalization for something specific, and allows an algorithm to work for multiple inputs. Abstraction is a key element of computational thinking and helps programmers in a multitude of ways. If you've programmed before, you'll recognize that in the Amaze Your Friends algorithm, the blanks could become a variable with a name such as last number. Result and sum are also variables because they represent values that change depending on the numbers in the sequence. A variable is an abstraction because rather than representing a specific number, it can be used to represent many different numbers. Classes and objects. Abstraction has uses other than identifying variables. It is important for understanding how to represent real-world and conceptual objects. Remember the pattern you discovered for social media login credentials? With a little modification, it becomes a template that can be applied to any subscriber. Class, login credentials. Attribute, user ID. Attribute, user password. Attribute, mobile number. The login credentials class is an abstraction that contains a set of attributes. The class was formed by abstracting away, or removing, details for any specific subscriber. Abstractions are handy for any programs that deal with real-world objects in addition to technology objects, such as login credentials. Black boxes. To drive a car, you don't have to know exactly what goes on under the hood. The engine is essentially a black box that you control using a few simple inputs such as the gas pedal, brake, and steering wheel. The details of the engine are hidden. In computer science terminology, these details have been abstracted away. See Figure 1-8. In concept, a black box is anything that accepts some type of input and performs a specific process to produce output without requiring an understanding of its internal workings. See Figure 1-9. The black box concept of abstraction is a fundamental aspect of computer science. Think about it. Computer programs are abstractions. For example, you can use a social media app without knowing anything about the programming that makes it work. The icons that you touch on the screen abstract away the details of the underlying programming. Programmers make extensive use of abstraction within programs by creating a set of instructions that functions like a black box. For example, you could bundle the instructions that handle login attempts into a black box like the one in Figure 1-10. Programming languages also have built-in abstractions that perform standard tasks. For example, the built-in random function generates a random number when given a range, such as 1-100. You can incorporate the random function in a program without knowing how it works internally. Levels of abstraction. After you get the hang of abstraction, you'll see examples of this computational thinking concept everywhere. Applying the correct level of abstraction to your programs may take a little practice. A level of abstraction relates to the amount of detail that is hidden. Abstracting out too much detail can make a program too generalized. Neglecting abstraction can produce programs that are too specific to work with a wide variety of data. See Figure 1-11. With experience, you'll be able to identify useful abstractions and gauge the correct level of abstraction to use. Module Review. Summary. Computational thinking techniques help programmers define problems, find solutions, delineate tasks, and devise algorithms. An algorithm is a series of steps for solving a problem or carrying out a task. Programming algorithms are the blueprints for computer programs. Standard algorithms exist for many computing tasks. When an algorithm does not exist, you can step through a process manually and record the steps, or apply computational thinking techniques, such as decomposition, pattern identification, and abstraction. Decomposition divides a complex problem or task into manageable units. Pattern identification reveals sequences and repetitive tasks that can lead to algorithm efficiencies. Abstraction is a key computer science concept that suppresses details, substitutes a generalization for something specific, and allows an algorithm to work for multiple inputs.